Hi, this is Mr. Goma. What we're going to do in this video is go over the worksheet on intermolecular forces. In particular, what we're going to focus on is question 6 on the back side of the worksheet. On question 6, we had to address two molecules, water, H2O, and carbon dioxide, CO2. And ultimately, we had to identify the kinds of intermolecular forces that each of the molecules experience. So let's go ahead and do that there. First, let's remind ourselves about the three kinds of intermolecular forces. The three kinds of intermolecular forces, or intermolecular, or IMFs, are dipole-dipole forces, hydrogen bonding, which is really just a subset of dipole-dipole forces, and London dispersion forces. So if you remember from this diagram here, if we only have nonpolar bonds, we're going to end up with a nonpolar molecule. This can also happen, a nonpolar molecule, if all of our polar bonds cancel out. Either way, if we have nonpolar molecules, the only IMF experienced is London dispersion forces, LDF. If you have a polar molecule, then you could have either dipole-dipole forces or hydrogen bonding. Hydrogen bonding occurs when you have an H, a hydrogen, bonded to an NO or F. If you remember, nitrogen, oxygen, and fluorine are the most electronegative elements. So bonds between hydrogen and nitrogen, oxygen, and fluorine are going to be the most polar bonds. So therefore, we have more polar bonds, we're going to have more polar molecules. All right, so let's go back to our worksheet and we can solve problem 6. Okay, so answer the questions for each of the molecules below. So water. Number 1, let's draw the Lewis dot diagram. Well, oxygen has 6 valence electrons, so we'll draw an O with 6 valence electrons. 1, 2, 3, 4, 5, 6. And there's going to be 2 hydrogens. 1, 2, each with 1 valence electron. Our bonds are going to be there. So water is H, O, H on the bottom. Note, water has this bent structure here. It does not have a straight line linear structure. So if you drew water with an HO and then an H over here, you will almost certainly get the wrong answer for the next part. Now, polar bonds. Let's go back and take a look at our periodic table. Hydrogen and oxygen. There's a big difference in electronegativity. Oxygen is the more electronegative element, so the electrons are going to get pulled towards oxygen. So let's go ahead and diagram that on our sheet here. And here. Okay, so now, what is this line referring to? This line refers to the electrons, or sorry, this arrow. This arrow refers to the electrons in this bond here. And this arrow refers to these electrons in this bond. It shows where the electrons are getting pulled. The electrons are still shared between the oxygen and hydrogen, but they're shared unequally. They're getting pulled towards the oxygen because oxygen is more electronegative. If electrons, which have a negative charge, are getting pulled towards oxygen, oxygen will have a partial negative charge. And therefore, the hydrogens will have partial positive charges. What we've showed here is that, yes, there are polar bonds, okay? So show the work below, I've actually showed the work right up here. Now, is the molecule polar? Remember, we're going to end up with a polar molecule if the polar bonds don't cancel out. And here, do they cancel out? No. Canceling out would be going in exact opposite directions. So like that, those canceling out, that's canceling out, exact opposites. So here, let me circle with a black marker. It's going to be yes for polar bonds, yes for polar molecule, because the polar bonds don't, can't write don't, there we go, cancel out. Okay, so now, last question here asks us to draw the Lewis dot diagram of two molecules with the charges labeled. Use partial negative, partial positive charges, if any, and the IMFs labeled if any. So let's go ahead and draw two water molecules right down here. So H, H2OH, remembering the bent structure on water. H2OH. 2 lone pairs, remembering the bent structure on water. So let's go ahead and label our partial charges. We'll label the oxygen, remember, is a partial negative because the electrons are getting pulled towards the oxygen. So electron are a negative charge, so the oxygen is going to have a partial negative. And the hydrogens have partial positive charges. So hydrogen, partial positive, partial positive, partial positive, and partial positive. Now, let's go back to our definition of an intermolecular force for a second. An intermolecular force is the force of attraction that pulls separate molecules together. Now, how do we get attraction? Well, you have to have opposite charges. And notice we need separate molecules. So we need opposite charges on separate molecules. So let's take a look here. Okay, so separate molecules, opposite charges. Well, look here. We've got a partial negative on this oxygen, partial positive on this hydrogen, negative, positive, opposite charges. So this is going to be the intermolecular force, IMF. What kind of intermolecular force do we have here? Well, we have a polar molecule, so it's got to be either dipole-dipole or hydrogen bonding. Let's double check. Well, hydrogen bonding occurs if we have an H bonded to an N, O, or F. Well, in water, it's H2O. So we have an H bonded to O. So yes, this is going to be hydrogen bonding. All right, so hydrogen bonding is going to be our intermolecular force. All right, great. So that's water. Now, let's take a look at carbon dioxide. Carbon dioxide is CO2. So let's go ahead and draw a CO2 here. So Lewis dot diagram for carbon, 4 valence electrons, 1, 2, 3, 4. Oxygens, 1, 2, 3, 4, 5, 6. Another oxygen, 1, 2, 3, 4, 5. I'll put this one over here, 6. All right, just like what we did over here, if we see unpaired electrons, we want to pair them up by sharing from 1 on each atom. So great, let's go ahead here. They can share. Notice, this oxygen still has another unpaired one that can share there. Let's go ahead and share these guys here and these guys here. So notice, there are going to be 2 pairs of electrons between the carbon and the oxygen and 2 pairs of electrons over here. So we're going to have O double bonded to the carbon, double bonded to the oxygen, lone pairs on the oxygen, lone pairs on the oxygen over here. Okay, let's go back and take a look. Next question, are there polar bonds? Well, if we look here, we'll notice that carbon and oxygen are separated on the periodic table. Oxygen is more electronegative, so the electrons are going to get pulled towards oxygen. Let's label that up. So electrons pulled towards oxygen here. Electrons pulled towards the oxygen here. Okay, so yes, we have polar bonds. And we showed the work up here. Now, is it a polar molecule? Well, look at these 2 polar bonds. They're pulling in exact opposite directions. So they're going to cancel out. So the answer is no, it's not going to be a polar molecule because the polar bonds do cancel out. Okay, now, so if it's a non-polar molecule, it's not a polar molecule, let's take a look at what kinds of intermolecular forces can be experienced. Well, let's take a look here. Go back to our example from the other video. If we have a nonpolar molecule, the only intermolecular forces experienced are London dispersion forces. We can't get dipole-dipole. Those only occur in polar molecules. We can't get hydrogen bonding. Those only occur in polar molecules where the H is bonded to N, O, or F. So we go back to our notes here. What can we do? So first off, we're not going to worry about labeling partial charges because we don't have a polar molecule. So I'm just going to put this like that. Okay. And I'll do another one over here. And there'll be some kind of IMF, all right? But it's going to be quite weak compared to the IMF in H2O. So I'll just go like that. And what kind of IMF is it? It's going to be London Dispersion Forces. Okay? Hope that helped.